Okay, welcome everybody. Is everybody able to hear me today? Alright, at least one. Okay, good. So let's continue on our Newton journey, chapter 5 and 6. But before we can handle Newton's first and second law, we need to go back to our favorite vectors and go over section C and D as mentioned on the schedule. So the first thing we need to do is revisit, or actually visit, position vector, unit vector, and equilibrium situation. So let's do that. So I'm going to go back to the vector page. We already mastered section A and B, so I'm going to go over revisit section B in vector. You've already went over this, but we never specifically talked about it, so let's summarize it. And especially equilibrium, which is an application of unit vector. And I will practice the two problems over there, and then we can port this into Newton's law. So first, let's revisit our calculus 3. So far, what we've done is we take the coordinate system as usual, such that x is perpendicular to y. You can do it in 3D. And we used to call vector with one letter, say vector A or vector B. What we want to do now is we want to prep ourselves for displacement, which was part of the definition of kinematics. So instead of calling a vector with one single letter, instead we're going to call vector in such a way that they go through 2 points. If we call point O the point at the origin, and let's set point A here, which has a coordinate of say 4 and 3, and then here point B, which has a coordinate of -1 and 2, then we're going to call the vector that goes from point O to point A as vector OA. Similarly, if we want to call the vector that starts at O and ends at B, again our little direction vector, our key, we're going to call this OB. And similarly, if you want to express the vector that goes from B to A, we start at B and we end at A. Therefore, we're going to call this PA. Of course, we're going to follow the same properties of vector. If BA is in this direction, it is very different from this vector because he has the same magnitude, but he has the opposite direction. Therefore, we're going to add a negative sign. Therefore, this is negative BA. Or, that's the cool thing about the position vector, we can swap the order of the two letters, and this becomes AB. Okay, so now the question is, how are we going to express the vector that goes through 2 points, that start at one point and end at the other? The recipe is easy. For OA, you're going to take the final minus the initial. So it's almost like a delta, which you've learned in calculus 1. Same principle. Always final minus initial. We don't care what's in between. So for the x component, it's going to be the x of A minus the x of O. And this will be the x component of position vector OA. And similarly, we're going to take the difference in the y. And if you have a 3D vector, you would add ZA minus ZO in the k direction. That's it. Very simple. So in this case, it would be 4. The nice thing about the origin is coordinate is 0, 0. 4 minus 0. And 3 minus 0. Hence, the coordinate of OA is, in shortcut notation, 4 and 3. Okay, so it's always final minus initial. If we apply the same recipe to position vector OB, then it would be -1 and 2. -1 minus 0, and then 2 minus 0. Now if we apply the same recipe to BA, again, we're going to take the final minus the initial. So it's going to be 4 minus -1, and then 3 minus 2. Therefore, it will end up with 5 and 1. Okay? How's everybody so far with respect to expressing a position vector, which is nothing else than a vector, regular vector, except this vector happens to go start at a particular point of known coordinate and end at another point of known coordinate. So you should have seen this by now in Calc 3. You should have all started vector analysis. So hopefully that should ring a bell. Now the great thing about position vector is now we can decompose those vectors. For example, BA can be decomposed as, instead of going from B to A directly, oh, I have a question. Should be both negative component, but no big deal. OB should be both negative. Oops, did I go somewhere? Oh, yeah, thank you. Yeah, that would match my figure. Thank you, thank you. So, and then, which means, thank you. Thank you, thank you. Third quadrant. Excellent. My mistake. The recipe and the formula doesn't change though. Okay, so now the great thing about position vector is we can squeeze any third guy in between. Let's say I'm going to squeeze O between B and A, and I'm going to separate them, which means that BA can also be written as BO plus OA. So that's the great thing about vectors. Graphically, instead of going from B to A directly from here to here, I can decompose it as BO plus OA. So from here to here, plus from here to here. Sure, the path is different. So that if we assign this to kinematics, the distance traveled is much longer, but the displacement is exactly the same. Okay, so let's check that we have the same answer. If OB is -1, -2, it means that BO, which is the opposite, is negative OB. Therefore, it better be 1 and 2. So let's add BO, 1 and 2, with OA, which was this one, 4 and 3, and we better get this guy. Sure enough, 4 plus 1 is 5, 2 plus 3 is 5. So the final displacement is always exactly the same. And the beauty of this is now you can decompose any vector, say BA, through either a third vector, or a third point, say D or E, or you can go twice. So you can go through 2 points if you want to. The advantage of decomposing a position vector through the origin is that the origin coordinate is very, very easy. It's always 0, 0. So really, when you write position vector OA, this is the same as the coordinate. Coordinate of A. Same thing. And OB is nothing else but the coordinate of B. So that's why using a position vector that starts at the origin gives us directly the corresponding coordinate of the point. Question so far on position vector? Okay, so let's continue. Let's use another page. Let's redraw our coordinate system. Now let's imagine that you have a line that goes through 2 points. Let's call this C and let's call this D. For simplicity, C is going to be on the y-axis, D is going to be on the x. So D is going to be, say, 4 and 0, and C is going to be 0 and -3. O is usually by convention origin. So we know right away that position vector OD is also for 0. Position vector OC is 0, -3. And similarly, position vector CD is going to be 4 and 3. And position vector DC will be -4, -3, opposites. Good. Now what is useful is, remember when we were decomposing vector, we consider those unit vector. And the convention was that if you pick the unit vector along the x, we call it I. If you pick the unit vector along the j axis, the y-axis, you call it j. And the reason why we do this is because we always decompose any vector that we had along the x and along the y. This allowed us, since our x and y axis are perpendicular to one another, to identify the right angle triangle and to use trig. So we can do the same thing, but now in any direction. Therefore, if you consider the position vector, say CD, which starts at C and ends at E, you can always figure out its unit vector. And its unit vector, by definition of a unit vector, is going to have a little hat. So we're going to call it ECD. That's going to be the vector that is in the same direction as your position vector. But the magnitude of this unit vector is going to be equal to 1, the same way as j and magnitude of I and magnitude of k was equal to 1. So it will follow the exact same property. So this property is always satisfied regardless of which unit vector you pick, either the one along the x or the one over the y or the z or any direction. But what's interesting now is, how can we obtain this unit vector for any position vector in any direction? The recipe is very easy, and it comes from the unit vector notation. We've talked about the component notation, which was that position vector CD was CDX and CDY. This is a great notation if you want to add this vector with another vector. The problem with this notation is, if you want to extract the magnitude and the direction, then you have 2 more steps to do. The magnitude is not clearly indicated here, neither the magnitude, neither the direction. So for you to get either the magnitude or direction, you have to do 2 more steps. You take the x component, you square it, you add it to the square of the y component, and you take the square root. Similarly, to extract the direction, you need to take the arctangent. And this only works in 2D. So another method of expressing a vector is to use what I will call the unit vector notation, which is to express the magnitude of the vector times its unit vector. This represents the magnitude, and this represents its direction, which is great, because then we can extract the magnitude very easily. It's right there. And the direction can be obtained as a unit vector in 1D, 2D, 3D, 4D, and D. So, if this is also another alternative to express a vector, let's solve for ECD. Since DC is the magnitude, which represents the length of a particular vector, it's not equal to 0. So we can divide both equations by CD. And therefore, we end up with ECD is equal to position vector CD divided by its own magnitude. That's the definition of a unit vector, and this is its property. It will work every time for any vector. Identify the vector that goes through 2 points, calculate the position vector. From there, we know how to calculate the magnitude. It's Pythagorean theorem, which works in n dimension, and we can always obtain the unit vector. So in this particular case, ECD will be position vector CD, so it's D minus C. So it's going to be 4 and 3 divided by 16 plus 9. Therefore, ECD is 4/5 and 3/5. This is a vector that has the exact same direction as position vector CD, but its length is 1. And you can always double check this. If you calculate the magnitude of ECD, you end up taking 4/5 squared plus 3/5 squared, and you take the square root. This will give you 1, because you're going to get 16 plus 9 divided by 25, and that's 1. So the square root of 1 will still give you 1. So it's a beauty. Everything is nicely consistent. So those are unit vectors. Very, very central, and again, you've seen in Clark by now. Those will be the only little guys that will allow you to survive the next class, C270, because everything will be in 3D, which means that you're going to move away from easy trig and start doing 3D type of thing, 3D decomposition. For us, it will help us identify the direction of some forces. For instance, let me use another board, but before we apply this, is there any question on the definition of unit vector and how we calculate it? Okie dokie, so let's apply this. Let's imagine you have a force. Let's pick a coordinate system again. You have a particular force that is in this direction, F. And you happen to know that this force is along a particular direction. If the direction is given to you in terms of an angle, we know how to do this. If we know its magnitude, we've done this before. We identified the right triangle that includes the angle. We pick the x component. We look at whether the x is adjacent to the angle or opposite to the angle. In this case, as we've done earlier, f will be f cosine and f sine. That works great in 2D, no problem. In 3D, you're going to run into trouble because now you're going to need 3 angles. We call them cosine angles. The angle between your vector and the x-axis, the angle between the vector and the y-axis, and the angle between your vector and the z-axis. Which means that you have to use Pythagorean theorem 3 times in 3 different directions, which is a nightmare. That's why we use calculus. So let's figure out if we can express f not using trig, by using unit vector, if instead of being given its direction in terms of an angle, we're given its direction in terms of a particular line that happens to go through 2 points, A and B. And let's imagine that from physical constraint, we know the position in A and B. Let's say A is equal to, let's not mess up, but Kyle is here to make sure I don't, -4 -2, yeah, B, what, 5 and 4. So, if we're being told that F is along the direction of AB, and again we know its magnitude, and we like to express it in terms of componentation to be able to add it up. First thing we need to do is plot AB. The position vector AB starts from A and ends at B. That's AB. We know that F is along the same direction as AB. But we don't know whether F is smaller or it could be bigger. It depends on this value. All we know is that they're parallel. But of course, they may have different magnitude. So if they may have different magnitude, for sure, we know that F is not equal to AB. That's a common mistake. So make sure you don't duplicate it. What we do know is that F is parallel to AB. This is what we can use. And if two vectors are parallel, due to the definition of unit vector, naturally they will share the same unit vector. The unit vector along AB is this vector, which has the length 1, and the unit vector of F is a vector along F, which I will call EF, and has also the length 1. So since unit vector have the property that they have always the same length, which is 1, and since AB is parallel to F, then of course EF is going to be parallel to EAB. So the directions are the same. And since the unit vectors, the magnitude are the same. So this statement that F is parallel to AB implies that EF is equal to EAB. And that's what we can use. Because now we can squeeze the definition in there. Definition of unit vector is the position vector divided by its own magnitude in general. Therefore, for F, it will be the force F divided by its own magnitude is equal to position vector AB divided by its own magnitude. And as you multiply both sides by F, you end up with this, F times AB EAB. And this is EAB, which is the same as EF. So we've just expressed F in component notation, and now we can calculate it entirely. AB will be 5 minus 4, so 9. Y will be 4 minus 2, so 6. We're going to multiply this by F and divide by its magnitude, 81 plus 36. So the x component of vector F will be, if you want to get to that, 9F with that stupid square root, and then 6F divided by that stupid square root. But usually we stop here. This is the direction of your vector F, and this is the magnitude. Both are nicely separated. We have expressed the direction in terms of unit vector, having x, y, j, how many directions and dimensions. And we have managed to separate the magnitude away from it. And the reason why we do this is because in physics and civil engineering, we are usually interested in magnitude. Because the direction we can obtain it from physical constraint. We can just look at the engine, take measurement, bing. We always get the direction of forces. Easy. What we're interested in is this magnitude. So the unit vector is essential for applied vector analysis. Okay? So the big thing is as you realize that the force that you're looking for is parallel and in the same direction as a position vector, then you want to express that vector in unit vector notation, which allows you to separate the magnitude from the direction, and you should be able to express the direction easily from the property of the position vector along which your force is aligned with, which allows you not to have to obtain the x, the y, and the z component of your vector, which is 1, 2, or 3 unknown. For us, usually in 2D, it's 2 unknown. But it will reduce us to just 1. Because if you know the direction, you know this part entirely. This is what you were looking for, instead of trying to look for the x and the y. So you reduce your problem from a 2 unknown situation to a 1 unknown situation, if you happen to know its direction, which will be very, very efficient in the future, especially in 3D. Okay? So let's keep that in mind, and let's apply it as we're going to see a situation that we call equilibrium. That's section C. Let's do the first problem. And let's warm up with the first problem before we tackle the second one, which will use position vector and initial vector, and unit vector, sorry. So let me bust up problem 1 on the board. Oops. Okay, that's our problem 1. So, we're given the situation where 3 vectors are given to us. They're all being drawn from the same point, but they don't have to. We're being given the coordinate system, no problem. We're being told that we know the magnitude of W, which is 4. And we're being asked to calculate the magnitude of the vector D and the magnitude of the vector R such that the system is at equilibrium. So the first thing we want to refresh ourselves is the first law of Newton, which stated, remember from last week, that the sum of the forces is equal to 0. This is equivalent to the keyword equilibrium. If you forget about forces and you consider vectors, then it's exactly the same thing. So really, the equilibrium condition in vector analysis is perfectly analog to the Newton's first law. So it's perfect. If we know how to deal with vectors, we know how to deal with Newton's first law. So you can imagine that if you were going to look at this from the top, say a force table, you're pulling with a particular along a string in that direction, somebody else is pulling along this particular string, somebody else is pulling along that string, you're all pulling together such that those directions are set. Then there will be a unique value for all those 3 forces such that the system remains at equilibrium. So either doesn't move or move at constant velocity. So that's the purpose of the game. So the first thing we need to make good notes of it is every time you see the keyword equilibrium, right away associate with Newton's first law or the vector analysis. The sum of all the vectors involved is going to be equal to the 0 vector. Don't forget the vector on the other side. If this is a vector, that's got to be a vector. So that's great. That's easy. It means pretty much all we're going to do is add a bunch of stupid vectors. We know how to do this. We know that for us to be able to add them up, we just need to express them in component addition. And we've practiced this in section A and B. Therefore, we know we need to express R in component addition, Rx, Ry. We need to express D in component addition, Dx, Dy. And we need to express W the exact same way. So really, all we have to do is use the skills that we obtained in the vector analysis chapter, section A and B. They're giving us a nice little diagram. So let's start with W. That's the easy one. W obviously is straight down. It's aligned with the y-axis. So what will be the component decomposition of W? Anybody? Let's review vector analysis. We've done this now 3 weeks ago, so that should be nice and easy. If you were going to express W in component addition, what would you get here? If we know that the magnitude is 4 and its direction is strictly along the y-axis and opposite to your positive y. Almost. Remember, the positive x is towards the right, positive y is up. Look at the direction of your vector W. It starts here and it goes down. Excellent. Always pay attention to your little arrows. They always give you the sign, right? Good. 0, -4. Now, to express the other vector in component addition, remember the rule, we need to figure out the angle between each vector and either the x or the y. Let's start with R. R is here. And in this case, to make the life easy, they're telling us the distance, magnitude of the direction between R and the negative x-axis. So we don't have to do that part. It's given to us. So we know for sure we can decompose vector R, so it includes that angle. Bang. So we're going to use the exact same technique as we've been doing it for the last 3 weeks. Decompose R along Rx first, Ry after. So that obviously Rx is the adjacent to the angle 45, therefore it's the cosine. And Ry is obviously the opposite to the angle 45, therefore sine. We don't know its magnitude, so we're just going to keep it in there. R is going to be unknown R times cosine 45 and R sine 45. And remember the last step of this process is to check the signs. Rx is going left, positive x is right, therefore this guy is negative. Ry is up, positive y is up, therefore we don't change that one. Alright, so nice review of section A. Decompose the vector in computation. Easy, easy. Let's do the same thing with D. Again, D is given to us very nicely with an angle that is defined from your vector and y. So right away, we decompose the vector D, such as dy first and dx after. We have a right angle triangle. Again, trivial, dy is the adjacent cosine, dx is the opposite sine, dy is positive, and dx is also positive. So D will be equal to D, which is still unknown, that's the magnitude, times the sine of 60, and the cosine of 60. Okay, so this is coming from section A and B. Let's review. The only new thing here is this part. Before we used to add vectors with each other. Now we know that if we add everybody up, we end up with 0. So this is almost the same, except R plus W plus D is equal to 0. Okay, so we don't add two vectors to obtain the resultant. We're trying to figure out the equivalent vector, either D or R, whatever you want to call it. So all we need to do is apply this in scalar. We have obtained our vector in component notation. We just add all the x component and add all the y component. That's it. So again, this is a 2D problem, two-dimensional problem. Therefore, this vector equation will give you two equations, two scalar equations. Those two matches because we need to figure out two unknown, R and D. So since the number of unknowns matches the number of equations, we're good to go. So really, this will give us two equations. Rx plus Wx plus Dx is equal to 0x. And Ry plus Wy plus Dy is equal to 0y. And that's it. Let's plug the value that we have from this, and we end up with 0 minus R cosine 45 plus D sine 60, and that's equal to 0. Similarly, negative 4 plus R sine 45 plus D cosine 60, and that's equal to 0. Bang! System of 2 by 2 from here. The rest is just math. We can get R and D. And remember, if we've done everything carefully and correctly, those two better be positive. It has to be positive. If you end up with a negative value, either there is a mistake here as you apply the condition of equilibrium, or there is a mistake as you decompose your vector, or this is wrong. And usually a negative sign here is most of the time, 99% of the time, due to the wrong direction of your vector. So you just flip it. Okay? So that's how we deal with the system of equilibrium, or at equilibrium. Right now we only did it with vectors. Now we can do the exact same problem by rephrasing it as if one person pull the string along or with a force W, a second person pull with another string along the force D, and the third one pull along the third string along R, what must be the magnitude of those three buggers such that the system remains at equilibrium? If you're taking the lab this semester, that's something you should have done by now on the force table. So that should be a nice review. questions? So again, from here, this is where you need to realize, okay, I'm facing a 2x2. That's high school algebra. If you know how to solve for this and you can do it fast, you're good to go. Make sure you practice. If you realize, I don't remember how to solve for this, make sure you go back to your high school math book and then go back to the substitution method or addition method or Cramer's method or determinants method, or Gauss's method, any of those 5. Whatever, use the one that you feel the most comfortable with, but make sure you practice it. If you don't want to review algebra, please purchase a calculator. You will always be able to use a calculator and use the RREF function or the determinant function or whatever function the calculator can do, so that you don't spend any time solving a 2x2 or a 3x3 or a 4x4 or a 5x5 and you get it right. The vector sum is 0, Crystal, but not the magnitude of D and R. If there were 0, the system would not be at equilibrium and the whole system will go in the direction of W. Does that make sense? Remember, we're looking for the magnitude of D and the magnitude of R. Excellent. Excellent question, though. That's exactly how vectors are not the same as scalar. This is true. This is equilibrium. But this does not imply this. That's not true in terms of magnitude. That can never be true in terms of magnitude because every magnitude are positive. So that's why we need to keep the vector notation, express all our vector in component notation or unit vector notation like we're going to see in the next problem, and then add them up the same way as we used to do in the past couple of weeks. Perfect. Alright, so now let's bust up the other example and see how the unit vector and position vector are going to show up. Let me use another board. Where is it? There we go. It's a similar problem. Actually, the exact same problem, except they changed the label. They're being told that the system is at equilibrium, which means right away, Newton's first law allows you to say that R plus T plus W is equal to 0. So that's the condition that we know. And what do they tell us? They must give us one of the 3. Oh, same thing, they're giving us the magnitude of W. So they can only ask for 2 unknown. They may give you, in this case, the magnitude and the direction of one of the 3 vectors, give you the direction of the other 2, and ask you to calculate the magnitude of the other 2. Or they could give you the magnitude and direction of 2 vectors, and then ask you to figure out the magnitude and the direction of the 3rd vector. The method is exactly the same. The only difference will be when you write your system of equations, then you will be looking for and solving for different variables. That's all. So, what is the difference between this situation and the previous situation? It is not a 3D, still a 2D. Oh yeah, you're right, it's a 3D. Thank you. Shit. Okay, so that's a 3D problem. Oh, no. It's a dot, Kyle. It's -4 and then 4.5. And then 5 and 2.5. You got me on that one. I was like, oh! Yes, Michael, we don't have the direction. Well, almost. We don't have the direction expressed in terms of angles. However, they're still giving us a direction of T and R. But how did they decide to give it to us? Not through angles. Exactly. Through points. Therefore, that's where we're going to use position vector. Now, Michael suggested, you know what? I don't care about position vector and I don't want to use them. Instead, I'm going to use the slope. And it's perfectly okay. Perfectly right. In 2D, you can bypass the whole position vector and just calculate the slope. That will give you exactly the same thing as the unit vector. This will always work in 2D. No problem. But then in 3D, you're going to have to go back and relearn that method anyway. Because again, in 3D, you need to use position vector and unit vector, or 4D, or 5D, or 6D. You won't be able to use a slope. Otherwise, you're going to have 3 slopes in 3D and 4 slopes in 4D. So in 2D, you can get away by never use that method. All I want to do is introduce it once in 2D, so that as you practice a similar problem in 3D, then you can survive and solve for it. And hopefully you will keep your notes, so that as you progress to the next class and you happen to take C270, then you'll be able to pass that class with not a problem. You'll have all the tools under your belt. So if we decide not to use a slope and stick with the position vector, let's use the same technique. We need to express those 3 vectors in component notation. W is trivial, same as before. T and R, let's use the same technique as before. We notice that vector T is parallel to position vector OA. Therefore, ET is equal to EOA. Hence, vector T is equal to its magnitude, which is what we're looking for, times OA divided by OA. And this is entirely known. Position vector OA is by definition 5 minus 0, and then 2.5 minus 0, divided by its own magnitude, which is 25 plus 25/4. Okay? So now you can express it in component notation, because you're going to add them up. This will be 5t divided by, okay, what do we have here? 4 and 4, so that's 125 divided by 4. That's the S component, and the Y component will be 2.5t. Bang! We have expressed t in component notation. We're ready to add it up with whatever other vector or forces we're dealing with. Let's do the same thing with R. R obviously is parallel to OB. Okay, so that's again the big first step that we need to pay attention to. Vector R is not the same as OB. Vector T is not the same as OA. We don't know the direction, the magnitude of T. That's what we're looking for. We don't know the magnitude of R. That's what we're looking for. So we cannot assume that the magnitude of T is the same as OA. But we know that T and OA share the same direction. Therefore, all we can write is that ER is the same as EOB. And then we plug the definition of unit vector. R divided by R is equal to OB divided by OB. Therefore, vector R is equal to its own magnitude times its direction, which can be expressed easily by position vector OB divided by its own magnitude. Let's use the exact same technique. OB is going to be B minus O, so negative 4 and 4.5, divided by negative 4 squared plus whatever that is. And again, we have expressed R in component notation. Negative 4R, we keep R as an unknown with that ugly square root, and then 4.5 times R divided by that ugly square root. Now we have to just express R in component notation. W was easy. We did it last time. Doesn't change. 0, negative 4. So now we can use the equilibrium condition as usual, add those three vectors. Those three vectors are in two-dimensional space, therefore we know we're going to get the sum of the x component is equal to 0, and then the sum of the y component is equal to 0, so we're going to get two equations. Tx is going to be 5t divided by 125 over 4, plus Rx is negative 4r divided by that ugly square root, and then Wx is 0. And then we add all the y component now, 2.5t, then the ty, and wy. Bang! That's a 2 by 2. We can solve for t, we can solve for r. Easy. And we know those two little buggers better be positive. Otherwise, we go somewhere. Okay? So, just by using vector analysis, we are able to handle any problem that can be analyzed by Newton's first law without doing any physics. Same thing. It's an exact analog. That's why vectors are so powerful, and that's why calculus 3 is so useful, especially that particular chapter. The first section that you may have seen was about conic. Circle, ellipses, blah blah blah. This can be a pain in the occulate. I don't know if you had to go with Porter. I hope you did. But this will become very, very useful if you're interested in going into celestial sciences. So NASA, SpaceX, everything is dealt with ellipses, parabola, hyperbola, such as orbits, change of orbits, or to be able to land on a particular surface of a particular planet. All this is all the mathematics that you need. Well, the good part of the mathematics that you need is the first section of Calc 3 that you may have used, or the conic section. And the second one is this one. Very, very useful. Questions so far? Everybody's so quiet. What's going on? Okay, so let's take a quick break, and then let's apply all this to Newton's problem. So I'm just going to go on the Newton's topic, and I'm going to go down the list. So Newton's law, homework. Let's start with NA1. So hopefully you started all those problems. They're a piece of cake. You most likely have done in 5 minutes, 10 minutes. As always, I'm going to spend half an hour because I want to go through the exact same method as the one that we laid out step by step last week, Wednesday. And hopefully you will see that if you stick to the method to solve all those problems, you're going to be fine. Those problems are very easy, but then they build in complexities. So usually what happens is people who decide not to follow the method can survive all the NA problem, the E problem, some of the output system and the PuTTY. And then when friction comes in, then they fall apart. And then as we add energy, they fall apart even more. And as we add rotation, that's it, they have to drop. But the people who start following the technique from the beginning, as we increase complexity, then they're fine. It's easy. They go step by step. Like you take a calculus class. Always go step by step. Don't skip any. So again, I'm going to solve all those problems very, very slowly by following all the steps that we laid out last week. I hope that you have it on a piece of paper, written in your own words, and that you're going to practice all those problems using that method. So I'm going to use the exact same method. And again, if you decide you don't want to use it, that's fine. But if you do decide to use it, then I'm going to be able to give you partial credits on the test. For WI folks, you have no choice but to use that method step by step. So we'll go through that. Let's take a quick break, 5:50, 10 minutes. Let's meet again at 6. And let's tackle and start and finish all the NA problem. Hopefully we're going to be able to start again all the E problem, which are an application of what we just talked about, which is equilibrium. And I'm going to release the boards so that if you need to review previous boards, Alright, so before we start, any questions on Newton? Any questions on the method that we went over last time? Remember that this method is laid out under the test link in case you want to go back to it and rewrite it on your own words. And any questions on position and or unit vectors? Okay, so let's start on, whoa, where's my pen? Oh, here. On first problem, NA1. We have an object sitting on an horizontal surface. Easiest case ever. Let's say what's given to us. An object of mass m2 kilograms. So units tells us m is the mass. Perfect. And it's resting on an horizontal surface. So this is horizontal. Of the magnitude of the normal force acting on this object. Okay, so let's follow Newton's method. First step. Can anybody give me an reminder of the first step of Newton's method? Excellent. Identify the system. Usually, the system that we identify is the one that has mass. So in this case, that's the guy. And remember, in Newton, it's nice. We don't care about the shape, so we can represent that method as a zero-dimensional point. Easy. We will lose this nice, easy simplification when we do rotation. But until we get to chapter 10, and we only take care about translation, because force is about translation and acceleration, linear acceleration, then we don't care. So that's nice. Perfect. So our block, or our object of mass 2 kilogram is our system. Second, what is the second step of Newton? You should all take notes, right? You should all have it on your notes. Cannot pass any class if you don't take notes. Please take notes. Yeah! Identify all the external forces. Thank you. External is important. That means they come from the surrounding and acting on our system. Good. Now let's go down to the list of the forces we've seen. What is the first one that comes to mind? Nope, that's not the first one. First one on the list. That was the second one. Michael, we've seen one before. The easiest of all. Yeah. The one that was the exception with respect to all the other, in the sense that this one acts at a distance, because it's one of the fundamental force of physics, 1 to 4. Newton's forces are not fundamental. They have to be contact forces. And we define that force as magnitude down, and direction down, sorry, and magnitude mg. All right. M being the mass, and g being the same g as we've seen in kinematic, which is positive 9.81 meters per second squared. Therefore, the product of kilogram for mass and meters per second squared for g gives us kilogram meter per second square as the units for weight. This is what we define as Newton. So if you're given everything in SI units, feel free to use Newton, so you don't have to carry out all those ugly units. The second one that comes to mind is the one that Michael suggested, normal force. What do we know about the normal force? By definition, what was the property of the normal force? Nope. They had nothing to do with gravity. But back to your notes. Yeah, perpendicular to the surface. That's the first property. Thank you, Dane and Mallory. The second property was that it is not only perpendicular to the surface, but because if it's perpendicular to the surface, it can be anywhere in that direction. The magnitude is not negative, but that's true for any force. Yeah, thank you, Michael. Because otherwise, it could be up or it could be down. They're both perpendicular to the surface. Which one is going to be? So we need to use the second part of the definition. It acts on our system. Since our system is right here and the surface is the one that creates the normal force, then that's the one that we need, not this one. This one will be the normal force created by our system on the floor. So that would be useful if we're studying the floor as our system. Perfect, so normal force is up. And it's perpendicular to the floor. Therefore, it's anti-parallel as the weight. Good. Do we know its magnitude? Is magnitude part of the definition of the normal force? When we went through the list. Excellent. Nope, we can never assume its magnitude. We will get the magnitude of n as we apply Newton. Never before. Even though in this case it's going to be trivial, as you will see. Good. What is the third type of force that we have listed? Excellent. Any pulling, pushing, spring, whatever. In this case, based on the two-line problem that are given to us, there is no mention of any other force that may pull, push. There is no mention of a spring. Therefore, the third type of force is 0. And the fourth type of forces that we've seen was friction. I remember we said that if you are not given neither the coefficient of static nor the coefficient of kinetic friction, US and UK, we can assume there is no friction. Perfect. So that's it. Only 2 forces. Good. First step 1 done, step 2 done. Third step. What is the third step that we need to do? Excellent. Free body diagram. The free body diagram had 3 components to it. Could you remind me of those 3 components? Essential components. A free body diagram needs to include all the external forces, excellent, with label. That's 1. There's 2 more. A coordinate system, excellent. And the third piece that most people like to skip, excellent, the direction of each of those stupid forces with respect to either our X or our Y axis. Perfect. So this is where the choice of the coordinate system will become essential. That's why I had you practice adding vectors in any coordinate system, because sometimes you may not want to pick X horizontal and Y vertical. You want to pick something that's flipped or transposed or rotated. In this case, you obviously want to pick one of the 2 axes, which is aligned along the most amount of forces that are given to you, that you have identified, because then it will simplify the decomposition of those vectors. Hence, let's pick Y, say up, and X horizontal. Let's double check the direction. The direction of N is trivial, it's along the Y, all done. And the direction of mg is trivial, it's also along the Y, the opposite direction, trivial. In this case, you don't even have to write it. It's only if it's not neither 0, 90, 180, or 270 that you want to show it. Perfect. Good. Third step done. That's it. Now we're being told to calculate, we're being told that the system is at rest. Therefore, it's at equilibrium. Therefore, we can use the first law. Based on our coordinate system, we only have to apply this first law along the y-axis, because there's only forces on the y-axis. Therefore, n component notation is n0, and the weight in component notation is 0n, sorry, and the weight is 0, negative mg. Therefore, as we apply Newton's first law in the y direction, we end up with n minus mg is equal to 0. That's where the science comes in, right here. And it's based on this. Problem is done. Now let's look at the problem. They asked to get the magnitude of the normal force. Bang, we saw for n. Question. There are only two cases in which a system can be at equilibrium, right? Possibly. Can you give me those two cases, just to be 100% clear? I believe you're right, but can you express those two cases? Where A is equal to 0 in both cases, that is correct. For both cases, A will be equal to 0, but velocity is above 0 or is equal to 0. That is correct. But it doesn't have to be above 0. It can be below 0 too. So you're right. The two cases are that if a system is at equilibrium, he can have a 0 velocity, which means it doesn't move. Or it could be moving at a particular velocity, but that velocity must be constant. But it could be in any direction. Therefore, it could be negative as well. But for both cases, the requirement that is common is that the acceleration is 0. Absolutely. Good. Does that answer your question? Or confirm it? Perfect. Yep. Excellent. So, as you can see, easy. Just be careful. This is an N for normal force, and this is another N for Newton. I know it's confusing, but if you don't like it, then call normal force NO or NOR, something. But remember that you always want to pick the units, put units at the end, so don't forget the units. I will never try to trick you by giving you gram or centimeter per second squared, or I'm always going to give you SI units. So if you like to use Newton instead of carrying kilogram meter per second squared, that's fine. Okay, now you plug numbers. M is 2, G is 9.8. So roughly 20 Newton is the magnitude of new normal force. Okay? Question on how we apply the method. Easy? Alright, so if you read NA2, can you go over the method yourself and tell me what will be different? Is there any step in NA2 that will be different? Is the free body diagram going to be different? Is the equation going to be different? And is the answer going to be different? And if so, where and how? So NA2 states that the object, same object of same mass, is now not sitting on the horizontal surface, but is moving at a constant velocity towards the right. So that's actually a question for you, Michael. Based on what we just clarified, can you tell us if there's going to be any difference in either the free body diagram or the equation or the answer for n? Excellent. If the system is moving at constant velocity towards the right, the system is still at equilibrium, and therefore everything is the same. Perfect. Excellent, excellent, excellent. That was the purpose of NA2, to help us remember that equilibrium does not mean that the system is static. That's only one possibility. The system could still be moving as long as you move at constant velocity. Thank you. Excellent. Any questions on the fact that NA2 is exactly the same as NA1? Again, it comes from the definition of kinematics. A is equal to dV/dt, as we clarified it last time. So, this question is also here to help us avoid the mistake and the temptation of adding a force along a particular velocity. Force is never associated with velocity. Neither acceleration. It's the net force. So it's not because you were being told that the system is moving and specifically accelerated in a particular direction that you need to invent a force in that direction. You don't have to. And most of the times, you cannot do it either. Stick to the list of forces. Because remember, it's the net force that is equal to the acceleration, not just one force. So always stick to the method and the list of those 4 forces. There's only 4 in this class, so it's easy. Then you don't take the risk of forgetting any or inventing new ones. All right. So NA2 done. NA3. Oh. It's like kissing my mother. It doesn't count. It's too easy. NA4. NA4, NA4, NA4. Up. So, in NA4, we're given the mass of our system, that little cube object, initially at rest. So at t is equal to 0, v is equal to 0. But then it is being subjected by a force F, which is given to us in magnitude, 7 Newton. That's the one shown here. So we know its magnitude and we know its direction. So obviously, this object is going to be accelerated. From Newton's law, if we ignore the Riemann sum, we would tend to think that, this object is accelerating in the same direction as F. So it would go up and right. But remember, Newton's law says that it's the net force. Sure enough, the question is telling us that this object is being accelerated along the horizontal only. So it's only in this direction it's being accelerated. So there must be some other forces to keep it there. Let's figure out those stupid forces. First, calculate the magnitude of the normal force as well as the magnitude of the acceleration, which is horizontal and towards the right. All right. So obviously we're looking for a force, we're looking for an acceleration. The law that comes to mind must be Newton's second law. It's a giveaway that we have to use the second one versus the first one because we're being asked that we're being told that it's being accelerated. Therefore, we cannot use the first law. And we're being asked what is its magnitude because they're giving us the direction. Perfect. So let's pick this as our system. Let's go through Newton's method. First, let's consider this as our system. We only have one system. This step is trivial. But let's make sure we don't skip it because as we're going to see composite system, that's going to be very, very relevant. Second, identify the external forces acting on this particular system. Let's go through a list. What is the first one that comes to mind? The weight. Excellent. The weight, since it's a force that acts at a distance, usually is applied at a center of mass, somewhere in the middle. We will learn how to calculate the stupid center of mass later on. Since we can neglect the size and the shape of the object, it doesn't matter. And since they're vectors, it won't matter because we can move them around. Good. Second one. What is the second force that comes to mind? Normal force. Excellent. Can you give me the direction of the normal force applied to this system based on the definition that we have, which has 2 properties? Excellent. Up. And usually this normal force comes from the surface, so it's applied right here. Perfect. Perpendicular to the surface. Good. Our object is in contact with only one surface, therefore there is only one normal force. There could be more than one if our system was in contact with more than one surface, or in contact with another object. All right. Third, any pulling or pushing? Well, obviously, we got one, F. This one is given to us. The third type is usually given to us, either in words in the problem or through a diagram if there is a little stupid spring. So the third one is F. F is applied to our system right here. It's in contact with the system right here. N is in contact with the system right here. And mg, again, is the only exception. Ex at a distance, therefore we usually put it at the center of mass. Somewhere in the middle. Good, that's the third one. Fourth one was friction. There is no mention of friction, therefore that's it. Good, easy. So, since we're doing Newton and we're only doing translation, let's make our life easy and use the property of vectors, which is that if you don't change neither their direction nor their magnitude, they're the same vectors. So let's plot all those vectors from the same point. mg, n, f. All right. Let's pick a coordinate system. Where would you like to choose your x and y axes? It's a free country, you can pick whatever you want. Since there's 20 of you, we could technically pick 20 different ones. Regular meaning x towards the right and y vertical? Alright. Since you never give me the positive direction of each, I'm going to pick y positive down and x positive, oh wait, left. Now, is that a good idea? At least it's not a good idea for one person. Why is this not going to be a good idea? It has to do with the physical constraint. I agree with you, Jamie. The y direction is fine. The x direction was a dumb idea. And it has to do with physical constraint. Yep, the weight is positive, but that's fine. As far as the y direction is concerned, it's fine. I'm talking about the x. Yep, it makes that force negative with respect to our coordinate system. But I'm talking about the x. Why is it a bad idea to have picked x towards the left? Based on physical constraint, based on what the system is actually doing, which is, read the question carefully, the first paragraph, third sentence. Third sentence. Wait, 1, 2, third sentence, yep. Yeah. They're telling us that the acceleration is horizontal. Based on this free body diagram, we know not only that it's horizontal, but we also know for sure that it's in which direction along the horizontal. Left or right? Right. Excellent. Which means that acceleration is that way. Yeah? Exactly, U2F. Now, an acceleration should never be part of your free body diagram. That always messes people up, so I put it on the side. But from what we know about vector, as I'm going to write Newton's second law, remember free fall, same situation. And we know that the acceleration is positive towards the right. And I decided to have positive x towards the left. What does that imply on the right-hand side of my equation? What do I have to do? From vector analysis. Remember, it's like when we did projectile motion. Free fall. Exactly. If we pick x positive left, then as we apply this, we are going to have to add a negative sign to our equation of Newton's second law. Which is fine. The problem is, half of us forget about it. Therefore, if your system is at equilibrium, write that down. That's part of the method. If the system is at equilibrium, which means it's either not moving or moving at constant velocity, the way that you pick your coordinate system, or your x and y axis, is that you try to choose this particular coordinate system such that the most amount of forces are aligned either your x or your y. Because then that will simplify their vector decomposition, right? As we've seen in the previous problem. Sometimes you can align 2, sometimes you can align 3. So go for it. Sometimes you can't. Nobody's perpendicular to one another, so it won't matter. But most of the times, you will have at least two forces perpendicular to one another. So if your system is at equilibrium, or moving at constant velocity, or velocity is 0 or constant velocity, that means your system is at equilibrium, pick your x and y such that the most amount of forces are along either your x or your y. But if your system is being accelerated, that means we cannot use Newton's first law, now we have to use Newton's second law. Make sure that you pick either your x or your y in their positive direction along the same direction as your acceleration. Because this will allow you to only write the left-hand side of Newton positive. You never have to worry about remembering to add the negative sign. Plus, as you will see in this problem, one of them will be 0. And we always love 0 because it makes the algebra easier. Okay? So make sure you write that down. If your system is at equilibrium, pick an axis such that the most amount of forces are either along the x or the y. And if your system is clearly accelerated in whatever direction, pick either your positive x or your positive y in that direction. Hence, I'm going to switch my positive x opposites so that it is exactly along my acceleration. This, right away, will tell me this. Sum of the forces in the x is equal to max, and this is positive. And sum of the forces in the y is equal to may. And what is may in this particular case? Due to my choice of the coordinate system, what is the y component of this vector along this coordinate system? Back to vector. Excellent. 0. Ding. One of the right-hand side will be 0. We love zeros. Well, except when they're downstairs. then they give us nightmare. But otherwise, we love them. Okay, so keep that in mind. It will simplify your algebra greatly and allow you to save so much time. All right, so we picked the coordinate system. We're good to go. We have our label. We're good to go. What is the last thing that we need to do? The last thing that is fundamental for us to deal with the left-hand side of Newton's second law, or first law. Before we do that, what are the 3 requirements of a complete free body diagram? First, our external forces with label. Second, our coordinate system, x and y, with a clear positive direction for each. And the last, which is the required condition for us to be able to express all those vectors in component notation, is same as the 2 previous problems. Somebody, who was it? Kyle, you're up. You're the one who gave us the answer previously. Yeah, directions. Excellent. Thank you, Jimmy. So, N obviously is trivial. It's along the Y. Mg, it's along the Y. No problem. F is the only one. So let's use whatever's being told in the problem or whatever diagram they give us to put the direction of F. In this case, they're giving us this angle. So the angle between F and the negative y-axis. We need this. We need this to express, I'm going to call it alpha, F in component notation. Because by identifying the direction, now it's easy. We know that the x component of F is sine, positive, and the y component of F is cosine and is negative. If we hadn't done this step, we'd be toast. Perfect. Now we write down the equation. So this set will give us this. The x component, F sine alpha is equal to ma. We can drop the subscript because the other one is 0. Bing. And we know that this is positive. We don't have to worry about it. So this choice of positive x makes our life easy. And in the y, we'll have mg minus n minus f cosine. So again, this step is chapter 2, vector. This is the science right here. This is vector analysis. So that was the first week. That's why we need to master this by now. And then the rest is high school algebra. Putsch. We can solve for n, we can solve for a. System of 2 by 2. Just math. So at this stage, I usually do everything analytically. If you don't like analytical solution, just plug numbers at this stage and then solve for it. Put in your calculator, bing bang boom. Otherwise, your value for the acceleration will be f sine alpha divided by m. You know f, you know m, boom. That's meters per second squared. And your normal force will be mg minus mg plus f cosine. And it better be positive. If your n end up being negative, you know you goof some. Whoa, I goofed somewhere. Yeah. If your n is negative, then we have problems. Okay? So as you can see, the magnitude of the normal force is rarely equal to the weight. So take that out of your mind, ever. We only know its direction. Okay? So what I'm trying to do here by following the method step by step, I'm going super slow, is to help you realize and appreciate that this is the key. If this is correct, nicely written, with colors if that helps you, with direction, the rest is easy, because from here to here is just math. It's just stupid vector analysis. You express all your forces in computation, you add them up, bing, bang, boom, done. This is where the only science comes in. And this is due to the choice of the coordinate system. As we have seen, AY is 0. And AX is entirely A in the right direction, which is a line along my positive X. Alright. So this is where Newton is cool, because finally we understand the value of the magnitude of the acceleration. In kinematic, we just took it for granted. A was equal to 9.81. Here, A is given by f sine alpha divided by m, whatever that is. F is 7, sine of 60 is 1/2, and 3 or so 6. So A is roughly 1 point something. The value and the magnitude of the acceleration is given to us by the net force. So the net force is causing the acceleration. And that's the great thing about physics. Physics is the only science when you can use causality. That's awesome. Any other branch of science, you're toast. You can only talk about correlation. Especially biology, environmental science, systems are way too complex. Physics is easy. Physics is always easy. It's the easiest. Especially if you can describe mathematically what's going on. If you can solve perfectly without making any approximation, then you can talk about causality. It's perfect. So a force causes an acceleration. So that means now we can appreciate why A is equal to 9.81. Let me show an example before we move to NA5. If you have an object, same situation as kinematics. It's here in the air, and it's going to be dropped. Therefore, it's going to be falling, right? Let's apply Newton to this little bugger. This is our system. What are the forces acting on this system? And this is not a trick question. You should be able to answer this within 2 seconds, right? What are the forces acting on the system that is falling down? Yeah, it's the weight. It's the first one on our list, right? Weight. Is our system, as it's falling, in contact? Same thing. Weight, gravity, same thing. I never pronounced the word gravity so far. I always use acceleration to gravity and weight. Gravity is in chapter 14. Is there any normal force acting on that system? Nope. Is there any other force that push or pull if we consider a free fall situation? Nope. There's no drag force. And obviously there's no friction. Therefore, this is only force. Well, let's pick a coordinate system. Let me pick X and Y. And let's apply Newton's law. Sum of the forces in the Y direction, and that shows Y to be positive because I know that my system is accelerated down. So this is equal to MAY. You could pick Y up. You're going to have just to carry a bunch of negative signs, Kyle. So I'm using the same technique as one before. I know my system is being accelerated down because it's a free fall situation. So I pick my Y in the same direction as A so that this is positive. But again, you don't have to as long as you put it there. Therefore, let's put the functional form of the only force that I have. It's the weight. Weight is equal to MA. What is the definition of weight? mg. mg is equal to ma. Let's solve for a. A is equal to g. And g is 9.81. That's where it comes from. That's why we call this the acceleration due to gravity. It's not gravity. It's just the fact that the force acting on your system is gravity and gravity only. Therefore, the magnitude of the acceleration picks up the value of g, which comes from the definition of the weight. That's the new definition that we have now from free fall. Before, the definition of free fall had 3 stages, right? The acceleration is constant, the acceleration is 9.81 meters per second, and its direction is down. That was the kinematic definition. Now we can complete it and rephrase it in a different way using forces. Free fall is when the only force acting on your system is the weight. Obviously, same thing. It will give us the 2 other properties of the free fall definition from kinematic. The beauty, everything is consistent. Okay? So we will see later on that weight is the same as gravity. The reason why I never use the word gravitational force or gravity, and I always use the word weight, is because weight is equal to mg. Gravity is equal to g, m prime over r squared. So which one would you like to use if you had the choice? This one or that one? Naturally, the first one. Much easier. So that's what we're going to consider. Okay. I thought we had a comedian. Yeah, second one is much more complicated. So the great thing about the surface of the Earth is that this F will reduce itself W. So the gravitational force will end up being equal to the weight at the surface of any planet. That's why when we do all those problems, we make sure that we are at the surface of any planet. Therefore, we can simplify our gravitational force and just call it weight, which is mg. Much easier. This is very, very complex. Okay? But we'll see that in chapter 14. And this, with energy, will, and already does, allow you to go to Mars. You don't need anything else but kinematic. Basic fundamental definition. Except you're going to use R, which is in any direction. Newton's law and energy. KE plus PE, as we will see later on. This is it. Chapter 2 and 3, Chapter 4 and 5, Chapter 6 and 7. All this is all you need to go to the moon and go to Mars. You don't need quantum mechanics. You don't need special relativity. You don't need quantum electrodynamics. You don't need string theory. Nobody needs string theory. That's not science. Just math. Beautiful, but not science. Easy. The equation that we need to use to go to Mars are the same from the 1960s. That haven't changed that much. So you could work for NASA right now. The only thing you need now is bust up your math, because the math is tricky. How to manipulate all those concepts in polar coordinates, in spherical coordinates, Cartesian coordinates, as you change orbit, as you land, and as you include drag force and all those little variation. That's where the math gets nasty. But conceptually, very easy. We can learn everything in this class. Okay? So, any questions so far? Any 1, any 2, any 3, any 4? And the justification of why free fall gives us a constant value for the acceleration to be 9.81 meters per second squared. All right. 5, 6. Okay, let's do 5. Common problem. This number 5 is good because it will help us revisit our geometry from high school, which will come back to us over and over and over and over, especially in C270 and C271. They're going to haunt you. So let's figure out another method to identify all those stupid angles. We have a little bugger on an inclined plane, like that. We know its mass given to us. We know alpha, that's the elevation of the inclined plane. And we're being told that it's being pushed along the plane by an horizontal force. So F is horizontal, but we don't know its magnitude. And the question is, okay, calculate the magnitude of F if that particular system, or the object of mass m, slides up the ramp with a constant velocity, and then deduce the normal force. What is, or what are, the essential keyword in this problem? Obviously, we're looking for a bunch of forces, therefore we know we have to use Newton. Which law are we going to use? The first, the second, or the third, and how are we going to know this? Because I don't see the word equilibrium in there. But there's other keywords. So Kala suggests we're going to use Newton's second law. Can you tell me why? Confirm by Menkel. Why? Give me keywords that confirm that choice. You should always know which law to use based on reading the problem carefully. So read the problem carefully, go sentence by sentence, and identify the keyword or words that will tell you which law. Do you see the keyword acceleration in the problem? Horizontal only gives you information about the direction of force F. Right? Force F shows up on the left-hand side. It's common for both first and Newton's second law. So that's not helpful. It's got to be something else. Both Newton's first and second law have the sum of the forces on the left-hand side, and horizontal force F is dealing with the left-hand side. So that's not helping. Can you be more specific? Which are the key word or words in that sentence that you pasted that confirms for sure that we have to use the first law? Excellent, thank you. Constant velocity means zero acceleration, means Newton's first law. Good. Never start a problem unless you know for sure which law to use. Good. So we know we're going to use the first law. All right. And we know that our system is moving up the ramp at a constant velocity. All right. So let's pick this as our system, and let's identify all the external forces acting on that system. Let's go down the list. What is the first one that comes to mind? The weight, excellent. Down. You can write it as W. Usually I write it as mg, so I save an equation. Up to you. Good. What else? Second one that comes to mind. Normal force, excellent. Normal force is perpendicular to the surface under my object. Therefore, it is, and is acting on my object. Therefore, the normal force is like that. And it's perpendicular to the surface. Okay, good. Third one, pulling, pushing. Well, obviously F is there. And it's horizontal. No friction is mentioned. That's it. That's all we have. Let's move all those little vectors, and we can do that by property of vectors, as long as we don't change either the direction or their magnitude, such that they all start from the same point. mg. This is my horizontal surface. This is my inclined plane. Therefore, my n is going to be perpendicular to this. And this is my F force. So always make a free body diagram that is perfect, nice, big, precise. Okay, next step. Pick a coordinate system. Which one do you want? Where do you want your positive x? And where do you want your positive y? Could you be more precise, Michael? What do you mean by Q1? Positive x align with F. Okay. Or I would use the normal setup. Okay. Okay. So we both agree. Okay. X and Y align with mg. Okay. Therefore, you want Y up. Okay. Like that. This is a good choice. Doesn't matter whether positive x is right or left because there is no acceleration. Similarly, it doesn't matter whether y is up or down because there is no acceleration. But it's a good choice to have picked x horizontal and y vertical because then f and mg are trivial as you are going to express it in componentation. So you only have to express one, which is n. And that's where we need geometry from high school. This is the angle alpha. Normal force is perpendicular to the inclined plane, which is measured from the angle alpha from the horizontal. So guarantee n depends on alpha. The question is, where is alpha? Is alpha between n and y, or is alpha between n and x? And that's where I'm stressing that the free body diagram needs to have those three components: force label, coordinate system, and direction. Because if you skip the direction part, how are you going to express n? No idea. And it's not trivial to figure out where alpha is. So think about this and let me know, where is alpha? Is alpha between n and y, or is alpha between n and x? And I'm going to skip that method, Jamie, of going from the positive x going counterclockwise. I'm going to use the method that I've been using since the beginning of the semester, which is to identify the angle between your vector and either x or y. So that angle must be less than 90. Exactly. So Jamie suggests between n and y is alpha. Is everybody in agreement with Jamie? If everybody is, or not saying anything, you're either lying or you're not listening. Because usually 80% of the people who say it twice don't see this. Are you really sure that you know for sure that the angle alpha is between n and y? I'm not kidding. And I'm sorry, I'm not saying you're liars. But this is a very common source of error. That's where most people goof right there. Kyle says not sure. I like that. Is there anybody else who think that they agree with Jimmy, but not 100% sure? Because if there is only Kyle, then I can talk to him during office hours and expect that you all know how to do this. I will never spend any time on it ever. But if there is more than one, then it's worth spending the time. Okay. To figure out where alpha is. Oh, okay, I'll wait. Michael, go for it. Oh, okay. So, can I go? Okay. And again, I'm being an ass. I apologize. The reason why I'm stopping here and want to make sure everybody is okay with this is I'm teaching 270 right now. And out of, how many bipeds is there? About 12 of them. Out of 12 students in that class, they're all taking Physics 170. They all passed Physics 170. There is 3 people who figure out where alpha is. 9 of them can't figure it out. So we have a big problem. So that's why I want to stress that out. The beauty of this is, again, there is a method for it. So if you stick to the method and apply it, you can never go wrong. If you're an expert in geometry, you don't need me. You can do your own thing. But just in case, here is how you would figure it out. It's a 2-step process, 2-step method. First, you stick and look at your vector of interest. In this case, it's n. And then you look at the 2 lines that creates the angle that you know is related to that force or vector. So in this case, there is a horizontal line and the line along the inclined plane. Identify the force of interest, that's n, and ask yourself, is the vector n perpendicular to the inclined plane or the horizontal? One of the two. It always has to be perpendicular to one of the two. Which one is it? Incline, because that's the property of the normal force. So just by the definition of normal force, we can answer the first question of that method, 2-step method. Perfect. So we know right away that this n is perpendicular to one of the 2 segments that creates our alpha, and it's this one. So let's forget about it, and let's focus on the other one that creates alpha. And the second question that we need to ask ourselves is this line perpendicular to your x or your y-axis? Which one is it? Is this horizontal line perpendicular to your x or your y-axis? Stay with me, Kyle. Next question. Is this line perpendicular to your x or y? Is everybody agree? It's obvious, right? Therefore, your angle is between your force and y. That's it. If the answer to the second question would be x, then the angle would be between your force and x. Now, let me address your question. Is it like rotating the x-axis all the way to where the y-axis is? I don't know. I think if you rotate your x and y-axis, the alpha is still in the same place. You wouldn't move around. Let's talk about this after, because I'm not sure what you have to hear. It would be the same if you rotate your axis. It wouldn't change. So those are the common things that you're going to see. This angle is the same as this angle. Very common high school geometry. Another one. This angle is the same as this angle. And by using this, is also the same as this, and also the same as that. So those are the ones you want to train your brain to identify. And the one we just did is this one. If this line is perpendicular to that one and this one is perpendicular to that one, the angles are the same. Okay, so all of those, all basic geometry. But, you know, it may be many years that you've seen it. Even more years that I've seen them. Because I'm old. So if you don't remember how to identify those or this, exactly the same thing. Or this, again, exactly the same thing. Sometimes it's not that trivial. You might take, you know, a couple of practice to have your brain recognize them. If you don't, and you're not sure, forget about them. The only one that really you should know is this one. But this one, forget about it, forget about it, forget about it, and use the technique we saw. Two-step process, two-question process. Identify the two lines that creates the limit of the angle that you know is associated with your force. In this case, we know it because we're dealing with the normal force and the angle that defines the inclined plane, and we know that normal force is perpendicular to the inclined plane. So guarantee alpha has something to do with n. So identify those two lines and ask yourself, is the force that I'm interested in perpendicular to this line or the other line? It's always one of the two. Once you have identified which one it is, nuke it. Forget about it and focus on the other one. And the second question you ask yourself is this leftover line perpendicular to my x? If it is, the angle is between your force and the x. If the other line is perpendicular to your y, then the angle is between your force and the y. You can never get it wrong if you follow this two-step process. And it's a little bit important because if you get the angle wrong, then I can just stop here. I don't have to look at any of the rest of your work. I know it's going to be wrong, and you cannot get any points. All right. Now that this is done, the rest is easy. We can apply Newton's first law. In both directions, x and y, therefore two equations. F minus n sine alpha is equal to 0. N cosine alpha minus mg is equal to 0. Again, this is chapter 2. So if you look at this and realize, whoa, how did you do all that? You know you're behind. That should take you 10 seconds, 10 seconds. Otherwise, you will never finish any test in this class. You need to go back to your vector analysis, express every vector in computation, bing, bang, boom, in like 2 seconds each, and then add them up. Okay? Because within a month of this class, you're going to have to do 2 or 3 free body diagrams. Therefore, 2 or 3 sets of 2 by 2. In C270, when you do trust, 5, 6, sometimes 7, still in 15 minutes. So you have to be expert at this. It needs to come naturally. So now we can solve for whatever we need to solve. What is the question? Stupid f, stupid n. Bah, easy. 2 by 2, we solve for n. mg divided by cosine alpha. That's the first one. Then we plug this in the first equation, and f is equal to mg tangent. Because sine divided by cosine is tangent. Done. Or, at this stage, plug numbers, enter any calculator, done. But you cannot waste time solving for a system of 2 by 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6. It's coming. Okay? 4 by 4 will come with friction. Before friction, we usually can get away with a 2 by 2, 3 by 3. But as you can see, the first 3 steps of Newton's are trivial. The only little trick here that we need to accustom our brain to get used to is to complete our free body diagram such that all the directions are expressed clearly for every force, because then you can do this step easily. And then the rest is just math. High school. Okay? Questions? All right. So On Wednesday, yeah, I will do either NA7 or NA8, just so that we see Newton's third law. And then I will complete the equilibrium set. We've already did 2 today. We just need to do 1 or 2 more. Done and easy. And hopefully I will start with Atwood. Okay? So that's where we're going for Wednesday. Unless we'll go a little bit later, then after the NA set and the equilibrium set, the E set, I will jump to the P set, pulley, because they're much shorter than Atwood. And then I will go back to AS set. Okay, so depending on how fast or how quickly or how slow we go. But by Wednesday, make sure that you complete all the NA problem and start the E problem. We should be able to do all the E problem based on what we've done on section C and D vector. And you should be able to start looking at Atwood and pulleys. But at least complete all the NA problem. Okay? Alright, and if you have not taken the test today, good luck tomorrow. And I'll see you on Wednesday. Let's take a quick break. And I want to see the WI folks, or rather what's left of them.